I joined Magic Leap a little bit ago, but I won't tell you anything about Magic Leap. But I will tell you a little bit about some other magic that's involved with this deep learning revolution that started a few years ago. So let's look at the sort of spectrum of machine intelligence over the last, say, 50 or so years. We started out by carefully teaching machines as to what we want them to do by sort of programming transistors to do all these gating functions, designing features, classification, and so forth. While sort of in the back of our minds, the ultimate goal is to just ask the computer to solve some problem and have it figure out what exactly it needs to do, how to design features, how to build intelligent pipelines, and essentially solve the problem and teach us as to what the process is like. The reality is we're about here right now. Maybe this is even a little bit too optimistic, but the latest and greatest in machine intelligence are in fact these deep learning models that allow us to achieve these great advances in computer vision, object recognition, speech, and following fields. So let's have a closer look at what deep learning has become over the last few years. So this is one of the original LeNet 5's convolutional neural networks that was introduced by Yann LeCun. This is from 1998. In 2012, a so-called AlexNet, developed by Alex Krzyzewski and Jeff Hinton in Toronto, sort of revolutionized this ImageNet competition and blew out traditional computer vision models out of the water. And finally, this is the GoogleNet, the mother of all networks, highly complicated system that we developed at Google about a year ago. So on one hand, these models are quite different, but on the other hand, they're all about the same, in the sense that they're all very difficult. They're all designed by humans who try to project the insights that they have about problems into these difficult architectures. And finally, they're all designed without a particular problem in mind, the problem that they want to solve. So all these networks essentially solve a general object recognition instance without having any data in mind. So essentially, all these networks boil down to this system where you have a network that learns some low-layer features that may be Gabor functions or some representations thereof, and then some higher-level features that a generalist system knows, where these are object parts of faces, cars, and so on. And then finally, at the top, you have this layer that gives you probabilistic labels. But what's important in this slide is that there's some structure to the output that's produced by this network. However, this structure is never utilized when these networks are designed. So the proposal is the following. Why don't we learn a system such that we start out with some network, whether it's LeNet, AlexNet, GoogleNet, or some other oracle. We give it the data that we want to use or to solve the problem with, look at the structure of the output produced by this oracle network, and then modify the network yet again to solve this specific problem. So rather than having humans come up with these highly complicated systems, we allow the data to drive the architecture of the network that will be used for this specific problem. So to reiterate, the constraints are we want the model to have depth and breadth and knowledge, essentially a mixture of experts. We want the model to understand the difference between a cow and an airplane, yet it needs to understand the difference between all possible airplanes there are, as same way as for cows. The design of these systems should be such that it needs to optimize learning in a way that is you reduce computation because you need these models to run in real time on very low power compute devices. However, you have to provide these models the capacity that they need to learn, but the only capacity needs to be provided in the places where it's required. So the general paradigm, just build the networks deeper, that doesn't apply for the reasons of overfitting and lack of data and many others. So to go back, if we look at the actual structure that you can learn from this oracle network, and you see this graph of labels in three-dimensional space where all the sort of classes and correlations between the classes is shown in color. And you can actually see that the network is learning dependence between the predictions that it's making. However, in traditional deep learning architecture design, this is not utilized. If you look even closer at this structure, you see that the system is learning things that are actually visually similar to one another. On the left, you see a bunch of different ships that are in the, I guess, in the top left corner. In the top right, you see all sorts of different looking foods that the system also co-confuses with each other, yet things are similar. And then on the bottom, you see some dog-specific breeds that are also looking the same. So the idea is you start out with the original Oracle network, whatever it may be. Then you learn some structure of the problem that you're trying to solve, and automatically you augment the existing network to produce this sort of a beast, which in fact is produced completely automatically, where there's a generalist part of the network that knows the difference between cows and airplanes. And then it's augmented with these specialized pathways. I won't say close to the way the brain works, because I don't know how that works. But these specialists, they come in different sizes and shapes. Some have more features, some have less. Some have more capacity, while others don't, because the problem they're trying to solve is much simpler. And at the end, the generalist and the specialist, they sort of compete with each other, and the preference is given to the one who has more confidence in the predictions they're making. So this kind of network works essentially with any Oracle and works for any data set that you can think of. We tried this on a number of examples, and here's just two of them. On the classic ImageNet challenge, where you have 1,000 classes. The small net, the red line is this old AlexNet. Then the orange line is the GoogleNet. And the green line, although the result may not seem significant, but it's actually rather important because you see an improvement over the entire range of recall. And furthermore, we don't increase any computation as shown in the right plot. We go from over 1.5 billion multiply ads to, we just increase the computation by 2% because we can't have models operate at larger lag. So we essentially take the exact same network, we reorganize it using the structure of the data of the problem that we're trying to solve, and we gain automatic improvements. Similar exercise was done with a Google internal data set that has, in this case, 17,000 classes, so it can tell you everything about everything. And here you want to look at the first two lines. We go from 36.8%, this is the GoogleNet network that won the ImageNet challenge this year, to almost 40% without increasing the computation of the network at all, yet by providing capacity only to the pathways that are more challenging for sub-problems than others. So what's in the future? So far, this is all very sort of intuitive, kind of hand-wavy explanations. There's a little bit of theory that supports all of this, but a lot more is needed, and we're working on the theoretical bounds of these new architectures. How much are they allowed? How much can they improve the existing results, and how much further can they be pushed? We're expanding this further to analyze video using recurrent neural networks and other architectures, not just for classification, but for detection, attention, and so forth. And finally, we want to build a system that actually teaches humans how to solve problems. Ideally, you just approach a machine as a black box, you tell it what the problem is, the system learns, and then it tells the humans what the problems are and how to solve it. So with this, I'll thank you, and that's it. By the way, we're hiring at Magic Leap, so talk to me if you want. Thanks.